Hi there, welcome back to thinktankonline. Learning. In this video, I'm going to talk about areas of surfaces in space. Okay, so if you're new to this channel, just click on the subscribe button and don't forget to turn on the notification bell so that you don't miss our next videos. Okay, so if you're looking for other videos like this one, you're going to go to thinktankonline learning information and go into the playlist section, and you're going to see the Mulitivariable calculus playlist. And when you click on that, you're going to see a lot of videos. I've got a plenty of videos which are hard to solve. Okay, so now what I need to do, we have to analyze our problem first. Okay, find the area of the part of the cone x squared equals to 3y squared plus 3z squared between x equals to root 3 and x equals to 2 root 3. Okay, so remember, given a cone, but our cone is not a normal cone. Okay, because you know that the equation of a cone is mostly in the form x squared is equals to z squared equals to x squared plus y squared, and that is the cone that we know. Okay, but this one is different, and you can see the boundaries are now in the x-axis. So what we're going to do, okay, so we're just going to change a little bit. We're just going to change your approach, but you're just going to use the same ordinary approach. Okay, so I have two methods of doing this question, and I feel like I'm going to show you both of them. So the first one is just going to use this general formula, and the last one we're going to use parametric equation. But I think the one for using parametric equation is very, very important, especially when you want to evaluate something like divergence theorem. To do the parametric sometimes always help. Okay, should try using some parametric equation because they save time, especially when dealing with more complicated questions. Okay, so now let's try to sketch this cone, but I don't know this cone. Okay, so what I'm going to do, I'm going to sketch my normal cone right here. Okay, so this is my z-axis right here, and this is my x-axis, and this is my y-axis. What does a normal cone look like? Okay, so the normal cone looks like this. Okay, so this is a normal cone. Okay, so since it has got a square root, we're going to have the other part on the downward here. Since say the square root of a number is either plus or minus. Okay, so now this is a common cone or ordinary cone. So how did I draw this cone? Okay, so remember, z is the subject of our formula. So in this case, x is the subject of the formula. Okay, so we have a clue. So what we're going to do, we're going to draw our axis like always. Okay, so this is the z-axis, and this is the x-axis, and this is the y-axis. But what is going to change is that our cone is now going to lie on this axis. Okay, like this. Okay, so I'm not going to draw the other part. Why am I not going to draw the other part? Because our boundaries for x, remember, given root 3 and 2 root 3, they're all positive. Okay, so I'm going to say this is the point where x is 2 root 3. I'm going to choose another point. So I'm going to choose this point. Let me say this is the point where x is equal to root 3, like that. So we're going to want to find the surface area. So this is the surface area of shapes that are in space. Okay, so this is the formula. Just going to find f of x squared plus f of y squared plus 1, and you need to find the square root. But remember, we only do this when z is subject to the formula. So in this case, our z is now our x. Okay, and no, it just doesn't sound good, but this is what we're going to do. So what you need to do is that let us write our equation. So our equation is now x squared is equal to 3y squared plus 3z squared. Okay, so let's make x equal to the formula. So this is going to be 3y squared plus 3z squared, or under the square root, like this. And what we're going to do, we now need to find f of x here. So now it's going to be x of, let me start with x of y. That means we're going to differentiate x with respect to y. Okay, so remember, this is same as saying 3y squared plus 3z squared to the power 1/2. And I would like to use this one since I'm differentiating. So first, let's find its respect to y. Like we've said, let's drop our power 1/2. Okay, the other thing, we're not concerned about z. Z is just a constant since we're integrating with respect to y. Actually, we're differentiating, I'm sorry. Okay, so it's going to be 1/2. And then we're going to have 3y squared plus 3z squared to the power 1 minus 1/2 minus 1. That's going to be 1, negative 1/2. Okay, but we have to multiply by the derivative of the inner. Okay, so the derivative right here is going to be 6y. Okay, that is good. Let's try to simplify here. So 2 into 6, that is going to give us 3. Okay, so that is going to be our answer. I'm assuming that you have a knowledge in indices. So if something is to the power negative half, to remove the negative, you have to say 1 over, and 1/2 means the square root. So I'm going to have 3y on top here, and I'm going to have 3y squared plus 3z squared, and I'm going to put a square root right here. Okay, so this is the partial derivative of x with respect to y. Now going to xz. Okay, now for xz, as you can see, this is it's just the same. We're just moving on to z, but z is also the same values as y. So I'm not going to waste your time, I'm just going to repeat that. So I'm going to write the 3, but in this case it's now z divided by 3y squared plus 3z squared. Okay, like this. Okay, so now we've done that part. So now let's go to x squared, to xy squared plus x z squared plus 1, or under the square root. Okay, so let's do that. Okay, so I'm going to write it right here. So for x squared plus y squared, so this is xy and this is xy, I'm going to say 3y over 3y squared plus 3z squared, or under the square root, and I'm going to put a square here, plus now I'm going to xz, this is going to be 3z divided by 3y squared plus 3z squared, or under the square root. And you should not forget this one, is very, very important. Okay, and we're going to write a square root right here. Okay, now what? Okay, so I think I've forgotten to put the bracket right here. Okay, so let's simplify. Let's simplify 3y squared, that is going to give us 9y squared, and this is square root. Remember, if we say root a squared, the answer will be a. So the answer here will be 3y squared plus 3z squared. Okay, and you're going to have, it's going to be the same here. It's going to be 9z squared divided by 3y squared plus 3z squared plus 1, and still you have that square root. Okay, now what do we need to do? These are the same denominator. Remember, when you say 1/2 plus 1/2, if the denominators are the same, just going to be 2 over 2. So it's going to be 9y squared plus 9z squared divided by 3y squared plus 3z squared, not forgetting the 1, and we're putting this under the square root. Okay, so as you can see, we can factorize here. Okay, we have 3 and we have 9. Let's do that. So we're going to have 9y squared plus z squared divided by 3y squared plus z squared plus 1, or under the square root. Okay, then what is going to happen? If we say 3 into 3, we're going to win. We're going to have 3 here, and this into this, we're going to have 1. Okay, so now we have the square root of 3 plus 1, and that is equal to 2. Okay, so let's go back to our formula and find the surface area. Okay, so for the surface area, it's going to be the double integral dy, and we're going to have root 2 here, and here I'm going to say dA. So this is going to be the surface area in space. Okay, but what I would like to do, I'd like to use cylindrical coordinates. I feel like they will ease my work other than using these rectangular coordinates. Okay, so remember, if we equate these lines with this equation, we're going to have a circle. Okay, so let's write it here. So we're going to have the first one, we're going to say x squared. Okay, x squared is equals to 3y squared plus 3z squared. Let's put root 3 here. So it's going to be 3 is equal to 3y squared plus 3z squared. So you can see, and this is going to be 1 is equals to y squared plus z squared. So this is the equation of a circle with radius 1. Now let's go to the second equation. Now our x is now 2 root 3. So this is going to be 2 root 3 squared is equal to 3y squared plus 3z squared. So we're going to have 4 times 3. Okay, so 4 times 3, that is going to give us 12, is equals to 3y squared plus 3z squared. If we divide each and every term by 3 right here, you're going to see you're going to have 4 is equals to y squared plus z squared, and this is a circle with radius 2. So these are our limits. Okay, you substitute x equals 2 root 3. If you say 2 squared, you're going to get 4. 4 times 3, that's going to give us 12. Okay, so now I'm going to draw my boundaries, these two circles, this one and this one, in the xy plane. So in the xy plane, I'm going to have a circle like this one. So the first one is a radius of 1. So this is the radius of 1, and the second one is a radius of 2. So this is the second circle, not forgetting to put my axis. So this is y, this is x, and we need to calculate the area of the region. So this is the region that we need. Okay, the region which is between. Okay, so now what is going to be the value of our angle? So remember, this is a full circle, so the value of theta is going to range from 0 to 2 pi, since it's now a full circle. Okay, so now we have to write our very simple double integral. So if theta ranges from 0 to 2 pi, and r, which is the radius, r, which is here, say that r ranges from 1 to 2. Okay, so r ranges from 1 to 2, and we have root 2 here, and instead of writing dy dx, we're going to use this Jacobian r dr d theta. Okay, so please make sure that you don't forget this r. Now let's integrate with respect to r first. Okay, so if we do that, what is going to be the answer? I'm going to say from 0 to 2 pi, and here I'm going to say 2r squared over 2. Just going to add the power divided by the new power, putting our limits 1 to 2, and we're going to have the theta since we haven't done anything about the angle. Okay, so now I'm going to say upper bound minus lower bound, 0 to 2 pi. So this is going to be 2 squared times 2, that's going to give us 8. Okay, divide this by this, okay, and just get 4 here to theta. Okay, and now integrate with respect to theta, this is going to be 4 theta from 0 to 2 pi, and if we do that, we're going to get 8 pi as our answer. Okay, so now I'm going to show you the second method. Okay, so like I said, on the second method, we're going to use parametric equation, and this method is very powerful. Okay, so you should be familiar with using parametric equation because these are going to help you, especially when you want to evaluate Stokes theorem, divergence. Okay, you are going to have some difficult complex, some difficult solids, and all we have to do is to ease them using parametric equations. Okay, so now what I was saying, okay, we're still doing what we have done in the first method. We have said that our diagram, I'm going to draw it again. I know that hard. Okay, so what we're going to do, we know that our parametric equation, z is equals to r cos theta. Remember, we've changed z. Then what about y? Okay, y is equal to r sine theta. Okay, like this. Now we're moving on to x. So x, from this we're going to see that x equals to 3y squared plus 3z squared, or under the square root. Okay, and what if we simplify here? We're going to say 3r squared sine squared theta plus 3r squared cos squared theta, or under the square root. Okay, like this. Okay, so now we're going to use the identity to know that this sine squared theta plus cos squared theta is going to equal to 1. So we're going to have the square root of 3r squared, and this is going to give us root r, since r squared has a square root. Okay, so now what do we need to do? We need now to draw our vector. Okay, so I'm going to put my vector, my parametric equation, in form of a vector. So that vector is going to contain theta, which is the angle, and we'll say theta ranges from 0 to 2 pi. Okay, then what else? I'm going to have r, which is the radius. Okay, so for the radius, say the limits are ranging from 2 to 2 root 3. Okay, like this. Now what do we need to do? We need to write our vector. So our vector is going to be, let me just say my vector is going to be vector v, which is a form of theta and r. So as for x, it's r. As for z, which is our x, it's going to be r cos theta, that is the I component, and for the j component, it's going to be r sine theta, and for the z component, which is going to be root 3 r. Okay, after this, what do we need to do? Okay, what we need to do is simple, because we want a formula. This is the formula we're going to use for areas of surface in space with the parametric equation. So you're going to have v theta, the cross product of v theta and vr. So this is going to be the magnitude. Okay, so here we need to find VR. So that means I'm just simply going to differentiate with respect to r. So I'm going to have cos theta here, and we're going to have sine theta here. I'm going to have, this is root 3r. Okay, so we're just going to have root 3. Okay, now let's move to v theta. Differentiating with respect to the theta. So you're going to have negative r sine theta, the derivative of cos theta. You're going to have negative r cos theta, and here we're going to have 0 since we don't have any theta here. Okay, so after that, one, to find the cross product of theta, of v theta and vr. So to find the cross product, just say jk, and we're going to put r sine theta here, we're going to put r cos theta here, and we're going to put 0 right here. After that, we're going to put cos theta here, and we're going to put sine theta here, and we're going to put 3. Okay, so something like this. Okay, so now let's evaluate. So first of all, starting with the j component. Okay, so I want to find the determinant of these things. We find this one and this one. So what we're going to say, we're going to say root 3r cos theta. That is what we're going to say. So it's going to be root 3r cos theta for the I component. Okay, now we're moving on to the j component. Okay, so for the j component, I'm going to be looking on this. Okay, so for the j component, so this is for the j component. We're now concerned about the determinant of this and this. Okay, so we have negative here, but automatically j component is a negative. Okay, so what we're going to write negative, and also have a negative, so it's going to be negative root 3 sine theta. Okay, like this one. Then now moving on to the last component, which is the k component. Okay, so for the k component, we're going to cancel here and cancel here, so we're going to find the determinant of this. So you're going to have negative r sine squared theta, since sine theta times sine theta is going to be sine squared theta, and minus this one, going to have negative r cos squared theta minus sine squared theta. So this is going to be our vectors for the cross product of v theta and vr. Okay, so what if we simplify? Let's simplify. You're going to have 3 root 3 cos theta, and you're going to have root 3 sine theta, and here if we factorize, factor out r, I'm going to say sine squared theta plus cos squared theta, and we're going to have r, which is negative. Okay, so this is v theta and vr. Okay, so now we need to find the magnitude of v theta times vr. Okay, so just simply going to square each and every component. Okay, so for r, you're going to have root 3 cos theta squared plus root 3 for y sine theta squared. Okay, and for r it's going to be r squared. Okay, like this one. Okay, so now let's simplify here. Okay, you should know that root 3 squared, that is going to give us 3. So we're going to have 3 cos squared theta plus 3 sine squared theta plus r squared, and we're going to put our square root. Now it's time with this identity. So if we say 3 cos squared theta plus 3 sine squared theta here, we're going to get 3. So we're going to have 3 here. Okay, but you should know that we have r okay, so I think from here you can see for the I component should have right r, so we have r here, and for the j also we have r. Okay, that same applies here, and the same applies here, so the same applies here and the same applies here. I'm sorry for that. Okay, so we're going to have, let's write it here and let's write it here. Okay, so now what we're going to have, if we square this one, going to say 3r squared theta and 3r squared theta right here. Okay, so we're going to have 3r squared theta plus r squared. Okay, so if you say 3r squared plus r squared, we're going to get 4r squared, and we have a square root, and the square root of 4 is 2, and the square root of r is r. As you can see, we now have the value of the cross product of v theta and vr. So our double integral is going to be, instead of writing this, we're now writing 2r, and we're going to write the theta, the r, the theta. Okay, so like what we did before, I'm not going to perform the integral since I've already done that. Okay, so thank you for watching. Don't forget to subscribe.